Welcome everybody in Introduction to Apache Spark Architecture. My name is Emil Kamiński, and today we will talk about the things like driver, workers, we will learn Spark UI, RDDs, transformation, and many other things. Basically, whenever you are planning to do any kind of data engineering job with Apache Spark, this is essential. But also, when you are working as a data scientist or data analyst, this knowledge will come handy. It will help you to troubleshoot some things or optimize your flows. And the way things are organized today, we will spend around 50% of our time talking about the theories. I have a couple of slides prepared for us, and a second 50% of the time, we will actually open Databricks and run a couple of queries, then open Spark UI and try to understand what was happening under the hood. Let's get started. First things first. If we open Apache Spark documentation, that's a definition we are going to get, and it's actually pretty important. Apache Spark is a unified computing engine and set of libraries for parallel data processing on the computer cluster. So why this is important? Well, first of all, Apache Spark was never designed as the storage system. The thing it do well is it takes the data from one place, do some magic, some transformation, and send it or save it to another place. The second thing, Spark really shine on the computer cluster, meaning whenever you have enough data that you need multiple machines to analyze it, Spark is the way to go. And the second way around, if you have a small amount of data which fits your personal computer, you have already better solutions than Apache Spark, even pandas in Python, and there is absolutely no need to learn Apache Spark. Now, talking about the libraries or module, actually the ecosystem of Spark is pretty rich. The first one and the most important is Spark SQL. This will allow us to write a SQL type queries to Apache Spark. Today we'll be doing that mainly with Python. We have also a module for stream processing, for distributed machine learning, for analyzing the graph databases. This is not really well developed module. And at the end we have something for R fans. So if you like to use language R, you have a dedicated module in Apache Spark which will allow you to use that language. And talking about languages, Apache Spark was mainly written in Scala, but you don't need to know Scala to use Apache Spark. You can use Java, Python, SQL, or R. There are some benefits of Scala, but in 99.999% of the cases, you don't need to use it. And if you don't even know what is it, you can think about the Scala like some kind of Java. It also runs on the Java virtual machine, on the JVM. And we can find Apache Spark in many different places. In Databricks, that's where the founders of Apache Spark works, but also in all main clouds, there is some kind of the flavor of Apache Spark. Let's talk about main components. I'm sure that you heard the terminology of driver and executor. So both of them are processes which run on the JVM, Java Virtual Machine, and usually driver and each executor is being run on the separated virtual machine for the sake of managing that and avoiding the conflicts. It can happen that we will have two executors on one virtual machine, but it's not common. And there is also a third very important element, which is called cluster manager, like Apache Yarn, Mesos, Kubernetes, or Spark standalone. And this is a component which guarantees delivery for us of executor and drivers, and we can run our application. So let's say that we have a data which we want to analyze, and we write application. We can write it in Scala, Java, Python, SQL, or R. So we write application, and application communicates with the driver through something what is called Spark session. That's the only entry point for us to Spark. Now, driver takes the application and try to figure out what we want to do with the data. Once it's figured out, and once it will figure out what's the most efficient way of doing that, executing that application, it will split it into the tasks which will distribute to the executors. And each executor can process in parallel multiple tasks, as many tasks as it has slots for the execution. And it will have as many slots for the execution as many CPU cores. So in our example, we have two executors. Both of them are having 4 CPU cores. Therefore, they are having 4 slots, and therefore they can process 4 tasks in parallel. Now, driver sent a task to the executor, and it also sent information which executor should analyze which part of the data. Then executors grab that data exchange the information between each other if there is such a need, and send the results to the driver, or save it to the files or send it somewhere else. Not always has to be sent back to the driver. So that's how the things looks on the very high level. So let's start looking into some examples, and after that we will jump to the Databricks and see how exactly the same example works in Apache UI. So let's say that we have an application which wanna count the number of the records in our dataset. And the dataset is of course represented by blue bars over here, and we have millions and millions of that rows. Our application communicates with the driver through a Spark session. Driver takes that application and analyze what's the optimum way of executing that, and also analyze a data, how much data we want to count, how many executors we have, and what is the most efficient way not only to execute an application, but also what is the most efficient way of distributing that data set to the executors. So it looks on the data and decide on how this should be splitted into something what is called partitions. Next, it sends the tasks to the executor to grab a different part of the data and assign it with the task to each and every slot. And in the slot 1, 2, and 3, we have a similar amount of data. In the slot number 4, we have less data. This is normal situation. Now, the first task will be to do a count locally on each slot. So executor starts to execute tasks. And it will happen that in this case, slot number 4 will finish first because it has the smallest number of the data. Then slot number 1, slot number 2, and slot number 3. In this case, all the tasks were successful. It can happen that some of the tasks will fail and the driver will need to reassign a task to another slot. But in our cases, all the tasks were successful. And we are halfway done. We have a local counts, but we don't have a final number. The next tasks, which driver will send to the executor, it will assign one executor to get all the data from all other slots and from all other executors, like in this example. And another task it will send to this executor will to perform a final count. And that will be the final count. And then, depends on the application, the instruction may be to send a data or save it to the file, and then there is no need to communicate the results to the driver. Or the instruction may be that give me the number because I want to display that to the user, and in such a case there will be additional communication happening between the executor and drivers, and the driver, in our case, we will just display that to the user. Let's discuss the big elephant in the room. During the examples, we will be using something that is called Spark UI, and we will be using that a lot. Spark UI is a really powerful tool, available by default on port 4040, which will allow us to understand many things which are happening under the hood and optimize our workloads. The thing is that it's not really modern looking, it's not really super intuitive starting from the day one, but for this or another crazy reason, once you will start using it, once you will start playing with it and try to understand what's displayed there, sooner or later it will become your second nature. Therefore, if you will not get it at the beginning, just absolutely don't worry, try to open it on your side and try to just follow me and you will be good. Okay, so we are now in the Databricks in our first notebook, where we are going to start exploring how Apache architecture really works. And first things first, we are using a small cluster with 2 workers. Each worker is having 8 GB of memory and 4 cores. So in total we have 16 GB of memory and 8 cores. And if we have 8 cores, it means that we have 8 slots. And the driver is the same, 8 GB and 4 cores. And at the beginning of each notebook, we are going to have a small setup. This is nothing what you want to have in the production, but whenever you are experimenting, you may want to have it. We are disabling caching data on the storage or on the workers nodes for the sake of consistency of each and every example which we'll be showing. We want every example to start fresh. So at the beginning, we are disabling caching. And a second thing is, this is our sample data for that notebook. In each notebook, we will be using fairly similar sample data, and this is available in each Databricks instances. It's examples of the data about New York City taxis and the trips, and that's how it looks like. We are going to have multiple files and its size, And the reason I like that file, I like that dataset, well, first of all, it's available in all Databricks instances. Second thing is that those files are fairly significant in size, like in this case, we have a data from 2009-07 and it's having 465 megabytes. So it's a good dataset to experiment with different performance and how different functions behave. And let's look on our first count example, so about 2009 data. And here we are using Spark to read all the CSV file from that location, which are about the year of 2009. So in total, we are reading approximately 5 gigabytes of data, and then we want Spark to count it. So let me run it. And what we are going to see is that Spark is actually starting something what is called job. We will be talking about jobs as well as the stages or the task later on in details, but we can see that straight away. This is the job number 0, it's a first job, the number starts from 0, and it's having one stage, also called stage 0. In that stage, we have one task to be run, and so far 0 has been completed. And once it will be completed, Spark will start a second job, also with one stage, but here we are having 12 tasks. And 8 are running in parallel because we have 8 slots. And as we can see, some task has been already completed. There can be basically two reasons for it. First of all, the partitions assigned to that task are smaller than for the rest of the tasks, or simply that slot is faster. So 8 tasks completed, 4 are running. And now we see that all the 12 tasks has been completed. There was one more additional job being triggered by Spark with only one task, but it was very fast. And now we can investigate further details in the Spark UI. There is multiple ways you can get into the Spark UI in the Databricks. You can go there by clicking those views, or you can go and click on your cluster, and then here you have a link to the Spark UI. We are going to have a Spark UI always open in the second tab, so we can quickly switch between it. And what we see by default is we see the number of the tabs on the top, like jobs, stages, and so on. The three the most interesting for us in a couple of next examples will be jobs, stages, and SQL/DataFrame. By default, I'm in the jobs. And in this tab, for the time being, I see 3 jobs, 2, 1, 0. And those are jobs which was visible over here, job 2, 1, and 0. And from here, we can already see some details about those jobs, meaning the duration of it. We see that the second job, the job number 1, took the most of the time, 1 minute. We see the number of the stages in each of that job, and we see the number of tasks in each job. This is the job which actually was the only one having more tasks than 1. So it would be nice to investigate further details about that job. Usually we will be focusing on the job which took the most of the time, and in our case it's this one. And we can do that very easily by clicking in the description over here. And it will take us to a bit of different view where we see something what is called DAG visualizations, which again will be explained in details later on, but it already gives us some idea what was happening in that job. At the beginning there was a scan of the CSV file, then there was some computation, later on it will be explained what the whole stage code again means, and then there was exchange. And whenever you are going to see exchange in the DAG visualization, it means that there was a data shuffling happening between the executors. So exchange always stands for the data shuffling. And if we scroll down, we see this stage. So we can also click on that stage and it will take us to further details. And now, as you can see, the tab on the top has been changed to stages, where we see that the total time across all tasks, it was 6.9 minutes, and the input size, so how many data we have read, and we read in our small application 5.7 gigabytes of data from the storage. And here we have again the DAG visualization, not so important, but once we will scroll down, this is super important, we are going to get the visualization of our task over a time. Each of that bar represents a task. And immediately from that view, we can figure out that we have 2 workers and each worker is having 4 CPUs. And the way we can figure this out is, first of all, the workers are very easy to spot. We have here a worker number 0 and the IP address, and the second worker. And in each worker, if we look closer, we have maximum 4 tasks being executed in parallel. Here it's very obvious, 1, 2, 3, 4. But the second worker is more interesting, 1, 2, 3, 4, but then another tasks are starting, but those tasks are starting only if there is previously other task finishing. So this task has started only when this task has finished. So if we take a look over here, we have 4 tasks in parallel. At any given moment of time, we are going to have 4 tasks being run in the parallel. Unless we are finishing the computation, then of course there will be less tasks. So this is a very interesting view and we'll be coming here pretty frequently. And once we are going to scroll down further, we are going to see another interesting data, this time summary metrics for 12 completed tasks. Here, those data we will be interpreting also frequently. If you don't follow at this stage, don't worry. In each and every example, we'll be coming here and explaining different part of everything what you see here over on the screen. And what I would like you to pay attention to is the input size record. That's basically the information about the size of the partition. And we see that the smallest partition assigned to the task, minimum, the smallest, was around 457 megabytes. And the maximum on the right, partition assigned to some task, was 540 megabytes. So just like in our example in the presentations, the partition may be different in size. And if we scroll down, then we see the aggregation metrics per executor, which is also very interesting. So we see that executor with the ID 0 has executed 4 tasks. It was also visible here. So here we have the 4 tasks. And second executor has executed 8 tasks. And the total memory read, here 2 gigabytes, here always almost 4 gigabytes. So also very interesting. And here we have the further details about each and every task, how big partition it got or how long time it took. In our cases, all the tasks have been successful. It may be that some task will fail, then a driver will assign that task and that partition to another executor, so we are going to have actually more tasks. But in our cases, everything was successful. And now let's go to another interesting tab, which is in the middle. It's called SQL/DataFrame, where we are going to see a bit of higher level, a bit of aggregated information of what happened. So in our cases here, we are going to have 2 entries. And on the right, you have information for which job each entry is and the duration. And we see that the job which took long time, it's over here in the first entry. So once I will click it, it will take us essentially to the same information, just represented a bit more differently. And this time we are reading that visualization from the bottom. So at the beginning, there was scan of the CSV files and the information about how much data we have read. Then moving up, there was a hash aggregate. And that was on our presentation the first time the count happened on each slot. So here we are doing the first count. And as the output records, we got 12 records. 12 records because we had 12 tasks and each of that task finished its job with 1 record. And then the next step is exchange, and exchange again, it's a data shuffling, it's moving data between the executors. So we see exchange happening, very small data being exchanged, of course. In this example, later on we are going to have examples where there will be a lot of data moving, and then final count happening over here, and the results are being sent to the driver for the sake of displaying that for us. So that's the whole idea. We will be talking about that in details shortly and explaining more things. Now moving back to our notebook, let's run a second example where this time we are running a data for 2009 and for 2010, so 1 year more, and I will hit Ctrl Enter to run it. And the idea will be the same. Spark will trigger a first job just like previously, which will be very fast and 1 task. Then the job number 4, and this is where it's interesting. We don't have any more 12 tasks. This time in that job, we will have 24 tasks. So far 0 completed, 8 running. And the idea is the same. Some tasks will finish earlier, some tasks will finish later. If some task will fail, then the total number of the task will be 25 or more. In our case, with so small number of data and so simple computation, I don't expect anything to fail. And here it comes. This job has been over, then was a third job, also very fast, 1 task. And this is a result displayed for us, meaning the data went through the driver for the sake of displaying that for the user. And if we go to the Spark UI to investigate job number 3, 4, and 5, and let's go to the tab Jobs. So we see that the job number 4 does the job which took the most of the time, 1.6 minutes with 24 tasks. Let me click on the details, and that's a DAG visualization. It looks exactly the same because the task basically it's the same, it's just volume of the data has changed slightly. And then by clicking on the stage number 5, it will take us to that nice visualization of the tasks. So right now we see that we have twice as many tasks, and now each executor has way more job to be done. And if we scroll down to the summary metrics for all those completed tasks, here the thing starts to becomes interesting because we see that the difference in size between the partitions, the smallest partition and the larger partition red, this is pretty significant. Here we have 300 megabytes and here we have over 500 megabytes, so the difference becomes really noticeable, and the summary of all the tasks. And for the sake of the exercise, let me go to the SQL and DataFrame tab to see how the things looks like over here. And the longest task, the longest jobs are over here, so I'm clicking on the description, and we can see that actually the execution is the same. So we are scanning CSV, just this time the volume of the data we're reading from the storage has almost doubled. And then we are doing the partial count on each slot, just like on our presentation. And the output rows is 24 because we have 24 tasks. Then we are doing the data shuffling, exchanging a bit more data being exchanged because a bit more tasks. Then we are doing the final count and we are returning results to the driver. So exactly the same idea. And as the last example in that notebook, just to show the contrast, let me read a single file from 2019 December. So that's significantly less data, but the structure of the application will be the same. First job very fast. Job number 7. Take a look on that. In this case, we have only one task. In this case, we were having only one task. In the first one, we were having 12, then 24, but now we have only one. So let's take a look on the details of the job number 7, stage number 9. And jobs number 7 took 8 seconds. And going into the details, we see stage number 9 looking exactly the same. Going to the stage number 9, 8 seconds, that's the data which has been read. If we scroll down, we see that there was only one task executed. It's because Apache Spark has decided that data is small enough, there is no point to split it across multiple partitions. He decided that it will be better to read it as the one partition, assign it to the task and get a job done. What is reflected over here? Summary metrics of one completed tasks, 114 megabytes, and also over here there is only one task. Okay, coming back to our notebook, that was the last example in this one. Key points to remember. Driver plans a job and make sure that those jobs are being executed. If executor fails, it will take a task and assign it to another executor. And what is important, driver almost never touches data. There are cases where it touches it, but generally it's avoid doing anything with the data. Otherwise, it will become very quickly a bottleneck. And executor execute a task and report the status to the driver. There can be more than one executor on worker node, but in case of the Databricks as well as majority of the Spark implementations, it will be one-to-one, one executor on one worker node. There is as many slots on the executor as CPU cores. There can be as many tasks executed by executor in parallel as many slots. Task is the smallest unit of work. This is a frequent question on Databricks exams. So for instance, if we have 2 workers, each 4 CPU cores, that gave us 8 tasks, which can be processed in parallel on those executors. Data are being split into one partition for one task, and the driver and the executor processes run on the Java virtual machine. By now, we were repeating a lot that a driver and executors sit on the separate virtual machines, which is not entirely true. There are other options. If we think about our own computer and then a data center or some virtual machines in the cloud, there can be actually 3 deployment modes. A local deployment mode It's something what allows you to install whole Spark on your computer, driver and the executor, and this setup is mainly for playing around, testing, debugging, maybe you want to develop something in such a setup. The second deployment mode is you can actually have a driver on your computer and executors in the cloud or in the data center, and this setup is good for developing something, testing, maybe interactive applications, but requires a good network connection between your computer and the data center. And the first setup, which is actually the only one which is suitable for the production workloads, is the cluster mode, which we were discussing so far, where a driver and executor sits in the data center in the cloud, and that's another frequent questions on the Databricks exams or Spark interviews. Let's talk about RDDs, data frames and dataset. Some time ago, when you wanted to write application which do something with the data, that data would be read into something what is called RDD, Resilient Distributed Dataset. And resilient means that it's immutable, meaning once created, it cannot be changed. If we would like to do something with the data, then the new RDD would be created. And this strange behavior helps Apache Spark to achieve fault tolerance. And then our application would interact with the data, as we are going to see in a second, through the RDD API, which first of all wasn't the most intuitive, second thing, it wasn't the best optimized. And then driver under the hood would take that RDD, split it into the partitions, and then assign tasks and partitions for the executors. Since 2015, we have two new APIs available for us. It's called Structured API or Spark SQL. One of it is called DataFrame, and we can use it in all the languages. Another one is something what we can use only in Scala. It's called Dataset, and this is basically the higher level API, meaning it's first of all, it's more intuitive, kind of looking like a SQL API, which is basically easier and faster to use than RDD. And the second thing, whenever we are using data frames and dataset instead of RDD, everything what we are going to write is being optimized by Catalyst Optimizer, and this is a big advantage over the RDD. We can still use the RDD API, but nowadays it's being considered as the low-level API. It gives us more control, but it's less intuitive, and it's not optimized by Spark by default. But we are going to see that in action. And we are now in the second notebook about RDDs, data frames and datasets, as understanding of those is important to understand Apache Spark architecture. Cluster is the same, many things are the same. What is changing is the dataset. So our task for that notebook is to use three of those, RDDs, DataFrame and Dataset, and find, using each of that, number of taxi trips per number of the passengers. And this is our dataset. It's the same as previously, just previously the files were compressed, and for the sake of making that easy to read into the RDD, I made a copy of one of these files, just it's uncompressed and it's ending with the CSV. And the data looks following. The logic behind it is not so important. The only thing worth paying attention to is the fourth column called passenger count with the number of the people in the taxi per trip. And now let's go straight to the first things first, and I need to prepare a setup. And now let's go straight to the RDD. So this is a reading and grouping and counting the data using the RDD. So at the beginning, this is the first difference. Previously, we were using a Spark session. In order to read the data into the RDD, I need to use something what is called Spark context. Then I'm using a function text file where I'm specifying, of course, what I want to read. And then we are going to see filters, maps, and reduce by key. So I'm filtering a rows and eliminating the row which contains vendor name. And the reason is because that's the first row which I don't want to take into my calculations. So I need to filter it in the RDDs. Then for each row, I'm splitting the data using a comma separation. And done with map, I am taking the fourth column and reducing by key just to generate a group by, and then I'm returning a final results to the variables count and trip count, and then I can print it. So let's press Ctrl Enter and see how this looks like in action. So you can see that it's not really a SQL like, it requires from you to learn the new concept when you want to use the RDDs, like those filter maps, which is more a functional programming style, not a SQL. But anyway, here comes the Spark job. And what we are going to see is that now we are going, for the first time, we are going to have one job with two stages. Previously, in all other examples, we were having multiple jobs, and in each job we were having mostly one stage. Here we are having one job with two stages, and in each stage we are having 5 tasks. So let's take a look on how this looks like in the Spark UI, job number 28. So let me open Spark UI, and here I have a job number 28. So let's take a look on the details. And we can see that something what is called DAG visualization, which we will explain, is showing right now 2 stages, and those 2 stages are connected, what means that there is data exchange happening between those 2 stages. And let's say that I would like to look into the further details, but using the SQL DataFrame tab. Here is the surprise waiting for me. There is no entry for the job number 28. So our job was number 28, and there is no entry here. And the reason is obvious. The RDD is the lower level API, not the higher level API, and that tab is dedicated only for the higher level aka SQL API, meaning whenever you are using a data frame, dataset, or you will be writing a SQL in the Databricks, you will have entry here. But if you will be using the RDD, which is lower level API, there will be no information about that over here. So the only information you can read about your application, in case you are using RDD, will be in the jobs or stages, which is natural consequences of Apache Spark architecture. So let's get back to our notebook. So that's how reading and grouping the data looks like in RDD. So we see that it's not so really intuitive. And now let's use a data frame. And with data frames, it's completely different story. It's basically day and night. So first we are reading a data using Spark session, Spark read option, and here we are reading straight away header, so it's simple as that, and specifying where the data we want to read is located. And then we are doing a SQL-like group by and count, which is fairly intuitive for everyone who knows SQL, and doing a show. Control Enter, and we can see that the application structure is immediately different. We are getting 2 jobs at this moment, and each job is having only one stage, this stage with 16 tasks. And we also get a third job with 1 task, and that's the results. And if we move back to the DataFrame SQL tab in the Spark UI, we are going to see those jobs over here, and we can investigate further details in the already familiar for us way. So that's basically what was happening. We were scanning CSV, doing the partial grouping, exchanging the data. And exchanging the data, what is important to say is that whenever we are exchanging a data, Spark is repartitioning the data which we are exchanging, and the default number of the partitions Spark is always trying to apply is 200, but then optimization, Spark optimization, which we'll be discussing later on, kicked off. It's compressed the number of the partitions to 1, it's performing the final grouping, and then the results goes to the driver. So that's the whole data frame example. So we see that first of all, it's way more intuitive to read. Secondly, we have this higher level API data available in the SQL/data frame. And the third thing is that one of the reasons for having multiple jobs with one stage over here versus one job with multiple stages in case of the RDD is that because of the data frames, there is a lot of optimizations happening, like catalyst optimizers and others, which we will discuss later on. So whatever we are doing in the data frame, it's way more better optimized than whenever using RDD. So the RDD is harder to use and it's less optimized. And now let's take a look on how the things looks like in dataset. So datasets are available only in Scala. So I need to define that starting from now, I'm going to use Scala as a language. And let me start from the second line actually. So here I am defining value dataset in the typical for Scala way. And then I'm using exactly the same way as in case of the data frames, Spark read option, CSV, and the path. So we can see that Spark is actually unified. No matter if you are using a data frame or dataset, many things will look exactly the same. Just at the end, I need to define the data structure which I'm expecting for the type safety purpose. And that's a big difference. So for that sake, I need to define a case class, which everybody who knows Java or Scala are familiar with. It's typically one-line definition of class where you are defining a column and the type, column and the time, and so on. So you need to define your whole data structure, and using that case class, you can read that data in the type-safety way to the data set. And then in exactly the same way as in case of the data frames, group by, count, and show. And what is important, again, that this is really a SQL-like program. Control Enter, and we see that even the structure of the application is exactly the same. We are going to get 3 jobs with 1 stage here, 1 stage here, and in the third job we are going to get 2 stages. One will be skipped completely, and the second one will be executed. And here it comes. That's the results. If we go again, this is job 32, 33, and 34. If we go to the Spark UI and let me refresh that tab, it's because we were using the higher level API. We have the details over here, and everything else looks exactly the same as in case of the data frame, just because we were using the case class and we were defining what data structure we are expecting. We achieved the type safety, and that's really the big difference. Okay, that was the last example for that notebook. Key points to remember, guys. The first one is RDD, which stands for Resilient Distributed Dataset, and it's immutable distributed collection of objects, which helps Apache Spark to achieve the fault tolerance, data lineage, and support a wide range of transformations and actions. Just the RDD API is not the most intuitive, as we have seen it. The second data structure is called DataFrame, inspired on pandas from Python. And DataFrame, it's a higher level abstraction over RDD, organizing data into named columns similar to the tables or to the spreadsheet. And whenever we are using a DataFrames, everything goes through Spark Catalyst Optimizer, which is a big benefit. And the third data structure is called Dataset, and this combines benefits of RDD and DataFrame, offering a strongly typed object-oriented API. That's why we can use it only in Scala and combine it with the optimization capabilities of the data frame. Let's talk about the transformations and actions. So basically in Apache Spark, there are 2 types of operations you can perform. It will be either transformation, either action. Transformation can be understood as a business logic you want to apply to your data. It takes one or more RDD, data frame, or data set and transform it into new. We were already repeating multiple times. RDD, data frames, and data sets are immutable. So whenever we want to do something with the data, it will create a new one. The original one will not be changed. And transformation, this is important, can be either narrow, either wide. Wide transformation requires shuffling data between the partitions, meaning exchange of the information between the executors. And example of the narrow transformation are filter, select, create new column, or cast. So let's say that we have a data distributed across multiple executors, and we call a function filter. Executors don't have to exchange any information between themselves. It will be enough if each executor will just filter a data which is having in his own memory and return the results. There is no need for exchanging the data. On the other hand, the examples of the wide transformations, such as group by, sort, and join, those require shuffling a data. And again, we can imagine data spread across multiple executors, and we calling a function sort. Then, in order to have a data properly sorted out, it will not be enough if each executor will sort only data which is having and then return the results, because data will be partially sorted. There need to be exchange of the data between the executors. So there need to be something what is called data shuffling happening, so we can sort all the data properly. And the last thing about the transformations are lazy by nature, meaning Spark will not do anything unless it will have to. And on the other hand, we have actions. Actions is a demand of results. For example, whenever we are calling a function collect, count, save, take, and show, this is basically information for Apache Spark. Okay, enough is enough. Execute all the transformations plus an action I have been asked you to do, and Spark will not wait any longer. It will execute everything what we have asked Apache Spark to do in our application. And we are in the third notebook about the transformations and actions, which are another cornerstone of Apache Spark architecture. And this is the shortest notebook we are having. We are having here only one query just to demonstrate the difference when we are having only transformations and when we are applying an action. So right now we are reading a data which we already know about New York City taxis. and we are applying our first transformation filter, and then we are applying our second transformation, which is select of two columns, and then we are doing the group by and some calculation. So this could create the impression that we are actually calling for an action, but at this stage we are not telling to the Apache Spark what do we want to do with the data. So if we run that, no computation will be kicked off. There will be, however, one small job over here, job number 47 with one stage, which will be super fast. It took 1 second or less. This job is not about the computation. If we look inside of that job, we will see that this job is really for a Spark to figure out what data we are talking about. It's not even about reading the data, it's just about figuring out how to partition that. So let me close that. And for the comparison, here we are having a three simple actions: show to display raw results to the screen, count to count the records, and the third one is actually more interesting. It's about writing the data, but in this case we are not going to write anything anywhere because we are specifying format noop, which is sort of fake. It's an information for Apache Spark that we are doing that just for the testing purposes. We don't want to save any data to the storage. And let me uncomment one of it, and the difference will be noticeable. While previously it took less than 1 second, right now it will take way more, and we can already see that we have more jobs. We have the same job as previously about figuring out the partitions, and then we are actually having the heavy duty job with the real computation. And now the whole application took 57 seconds because only now the data has been read and the calculation have been executed, and that's it for that notebook. Jobs, stages and tasks. So every time we supply application to the driver will split our application into one or more jobs. Jobs can be run in parallel, but it's under some circumstances, but usually it will be run one after another. Inside each job, we have one or more stages. What is important to remember is that stage 2 can start only once the stage 1 will be finished. There are again some special cases where they can slightly overlap, but the general rule is that stage 2 will start after stage 1 will be finished. And inside each stage we have multiple tasks or one or more, and we can run as many tasks in parallel as executors CPU cores, that we already know. And the reason for stages to happening one after another is because Apache Spark tried to compact all the transformations which does not require data shuffling into one stage. So all the narrow transformations like a filter or creating the new column. And then only when the data shuffling is required, then the new stage will be created. So the data shuffling is a boundary between the stages. And now, each job is represented by something what is called directed acyclic graph. In short, DAG. And it's called like that because it's only one direction. And in this case on the right, we have very simple example of DAG with two stages. Stage number 10, then the data shuffling is happening, and stage number 11. Even we have here information that the exchange is happening, so this is also information for us that the data shuffling is happening over here. And before seeing that in practice, let's discuss one more time laziness of Spark. So let's say that we have very simple application which is reading some data, and already at that stage Spark will or can fire very small job to figure out which data we are talking about, where are the files, what files we are talking about, how much data there is. And let's say that in our application we want to group by something this data and then perform another wide transformation, maybe sort, maybe join, and then filter data. And then we are asking Apache Spark to show us the results. So Apache Spark is smart enough to identify this guy and to figure out that it will be way more efficient to push that guy as much as possible to the left. And the reason being is by doing that, Apache Spark can limit a data we are reading. Maybe data are being partitioned, maybe instead of filter we are using a select and data are in packets, so Apache Spark will only read a specific columns, but basically Apache Spark will try to limit as much data as possible, so the further transformation, the wide transformations, will have less job to be done. And then, of course, show is happening, so action, and Apache Spark will fire a jobs, in our case, job number 1, and second job number 2. And this laziness of transformation is one of the principles of Apache Spark architecture. And we are in the fourth notebook, jobs and laziness according to Apache Spark architecture. And this will be a combination of the things which we already know very well with some new stuff. So let's talk first about DAGs. Here we have a query from the previous notebook where we are reading a data, applying a filter, select, doing a group by, and then an action show. And in our case, the query has been already executed and we can figure out part of the DAG already starting from here. We see that we have 3 jobs and 4 stages. If we go to the Spark UI and we find, for instance, a job 63, we can figure out a DAG over here. So 63, and that's a DAG for that job. If we remember the RDD, we didn't have multiple jobs, but we had a one job with multiple stages, so we could see all the stages in one place. In case of the data frame, like right now, we have different jobs, and if we want to have the holistic view, we need to go to different stages and figure out the different part of the application over there, like to job number 65, and figure out this part of the DAG, or the DAG for this job over here. Another way on looking on the DAG is to go to SQL DataFrames Tab. Just this time we don't get exactly a DAG, but something what is called a plan. And we already know plan very well. It looks like following, and the way we read it is from the bottom, because that's the only way really you can do that properly. But if we scroll down, we see very interesting thing over here, details, and if we expand it, we see something what is a bit scary at the beginning, but it's actually very intuitive and useful. This is the post-execution details of what Spark has been done. Under the physical plan, we see what steps Apache Spark has been done. We also see the initial plan. The difference between that we will discuss in a moment when we will be talking about the Catalyst Optimizer. And if we scroll down to the bottom, we see further details about the plan. And actually, what we see here at the beginning, it's very useful, but we don't need to wait for the execution to happen. We can actually figure out this plan and at the same time have a pretty good idea about DAG straight from the place where we are writing our code. And for that, we don't need any action. If I comment show, so we have only transformations, and I use a function explain, Control Enter, I am going to get, well, one simple job because Spark is trying to figure out the data again, but then we are going to get a physical plan as Spark believes it will looks like. And the way to read it is from the bottom again. So at the beginning we are doing the file scan, and we can see that Apache Spark is trying to extract only the columns which will be needed for the computation. If we were using as a dataset a Parquet files or Delta format, Spark would be actually successful and would read only those columns, but because we are reading the CSV, Spark needs to read the whole dataset anyway. Then Spark is applying our first filter over here, checking if the passenger count, that's the filter. Checking if the passenger count is not null, and checking if the passenger count equals to 1, as we've written in the query. Then we've written in the query select, and the same is happening over here, just it's called project, trip distance and payment type. Then we see the first calculation, hash aggregate, so group by happening on the separate slots. We see exchange, and we already know very well that exchange is about the data shuffling. And then we see the final group by, and that's the whole plan as Spark see it before executing actually the query. Of course, it may happen that in case of the big complex applications, while the execution is happening, Spark will collect more data about the execution and it will decide to change the execution plan on the fly. But in majority of the cases, this plan displayed with the function explain, this is actually fairly similar to what you are going to expect to see at the end of the execution. And let's now talk about the laziness. I just need to change comments over here. So this is the same query as above, and this is going to give us exactly physical plan as before. It's exactly the same. And now what I want to do is I want to add one more transformation over here, one more filter to the whole query. And here comes the beauty of the laziness. Because Apache Spark is not executing anything every time we are giving him a transformation like here, here, or here, but waiting for an action, Spark will actually catch the fact that we are doing a transformation which he can push closer to the source, and he will optimize the query for us. Let me hit Ctrl Enter and let's see where this filter with payment type equals to cash will be pushed. So Ctrl Enter. And as we can see, instead of adding the filter at the end of the execution, Spark is actually pushing that filter and combining that with the same filter as we have before, with the filter about the passenger counts. And now we are filtering not only passenger counts equals to null, but also adding payment types equal to null, and the same passenger count equals to 1 and payment type equals to cash. Apache Spark used the opportunity of being actually lazy, and before us hitting and adding any actions, it actually optimized all the operations we are expecting him to do. Let me add to this one more thing. The function explain is having actually very useful parameter, which is called true. And once you will be learning Apache Spark more and more, you will be using that function pretty frequently. Let me keep the same query and push Ctrl Enter right now. The difference is that right now, besides of the physical plan, which I got before, I'm also getting other plans, the earlier plans, and if I scroll to the top, I see something what is called parse logical plan, meaning that would Apache Spark ask us if it wouldn't be lazy. It would read the data, apply the first filter, apply the first select, group by, and the second filter at the top. That would happen if Apache Spark would execute the query as we are asking him to do. But because of the Catalyst optimizer, which we'll be discussing later on, it was successful to go through a couple of optimization stages and push it closer to the source. That's it for that notebook. Data shuffling. So why do we care about data shuffling? We are talking about it pretty a lot. So data shuffling is a process of redistributing data across partitions and typically involves data exchange between executor nodes. We already know that. And wide transformations require shuffling, of course. So, for example, whenever we have narrow transformation, and we can imagine that this is our cluster of executors, when we want to apply a transformation like a filter, which is narrow, each executor can take data which is having already in memory and just apply a filter. It doesn't need to have any other data from any other executors. And in contrast, when we want to perform a wide transformations like a join or sort or group by, then each executor to perform that task properly needs data from other executors, so we are exchanging a data. And the problem is that the beauty of Spark is because it's processing a data in memory. That's another fundamental principle of Apache Spark architecture. And that's why it's so fast. And whenever we are talking about the data shuffling, we need to take that data from the memory, save it to the storage, send it over the wire to the storage, and then again read it to the memory. And those operations are significantly slower than just in-memory processing. Sometimes you can avoid it, like for instance, avoiding making unnecessary sorts or optimizing some joins or filtering some data early on, but frequently we shouldn't go crazy about the data shuffling. We should be aware of it, we should be aware when in our code it's happening, but just sometimes we will not avoid it. And before jumping into Databricks, let's take a look on one more example. Let's say that we want to group by and count our data, and different colors represents different category of data. So at the beginning, driver is deciding on how to split the data into the partitions. Then each executor is grabbing their part of the data and perform a local group by and count. But shortly, executors are hitting the wall, and in order to continue, they need to do a data shuffling, so the new stage is required. The data is being exchanged, and only then executors are able to continue with their task and perform the final counts, and here comes the results. And we are in another notebook, this one about the data shuffling. And the reason we are here, well, actually there are three reasons. First of all is to see how you can recognize a data shuffling in Apache Spark UI. The second reason is to see the impact of data shuffling on the performance. And the third thing is to see that the data shuffling does not only depend on the type of the transformation we want to apply to the data, but also on the data itself. So knowing a data, it's always a good thing. What is different is that most of the queries in this notebook has been already executed by me. It's because they take a bit of time and to make it faster. The data we are using is a data which we already know and like about New York City taxi. That's how it looks like. We will use a couple of columns like a pickup date, payment type, and fare amount. And the first query is following. We are reading the data for 2 years, so we are going to get around 5 gigabytes. And then we are doing a very simple group by a payment type and doing a count. And if we take a closer look on the payment type, we are going to see that we have only 2 options over here. Someone paid either by credit or by cash. And this type of the column is called low cardinality column because there is very few options. And if we run explain, then we are going to see no surprises over here. That we are doing the file scan, then we are doing the first group by, then exchange, and every time we see exchange, we already know what it means. Data shuffling, and then final group by. And after executing the query, that's the query execution. The action is writing the data, but it's a fake writing because the format is nope. That's the results. We're having 3 jobs. And we can go to the Spark UI and take a closer look on those jobs and how to recognize the data shuffling. It was 3, 4, and 5. If we check the execution time, job number 4 was the one which took the most of the time. So let's go and see the details of it. And once I will scroll down, I can see over here on the right, shuffle write. This is basically the information how much data has been written to the storage, to the drive, for the purpose of shuffling. This time it's not a big number, it's 125 kilobytes, and we can see further details by clicking on the stage description, scrolling down, and we also have a statistics. What was the minimum volume of data written by single task to the storage, and what was the biggest volume of the data written to the storage by a task, 86 kilobytes, so a bit more. And if we scroll down, we can also see the details by a task. So that was the task which wrote the most, and if I sorted the second direction, this wrote way less. Okay, let me keep that tab open and let me scroll down to the second query. So here we are having exactly the same query. What is different is the column on which we are doing the group by. So previously we were grouping by payment type, now we are grouping by fair amount, and if we look on the data, this is higher cardinality column because we have way more options over here than a payment type. And again, checking the execution of that query, job 6, 7, and 8. So let me go to the Spark UI and find those jobs, 6, 7, 8. 6, 7, 8. So job number 7 was the one which took the most of the time. Let's see the details. And we see that shuffle write, nothing big, 1044 kilobytes. And going into the details of the stage, we are probably going to see some small change over here. So the minimum was 40 kilobytes written by a task and maximum was 50, not a big deal if we compare it with the previous one. Well, more or less the same. We are still talking about very small number of data written to the disk. It's not rather anything impacting the performance. But let me now get back to the notebook and let's do exactly the same query, just this time using the pickup date time. And if we check the data, pickup date time, it's somewhere on the left. Pickup date time. So we see that this is really the high cardinality column. There will be very few values which are like this one. Okay, this one is happening twice, but usually each and every value will appear only once. So this is the high cardinality column. And going back to our query, as the results we got job number 9, 10, and 11. Let's find them in the Spark UI. 9, 10, and 11. So job 10 was the one which was taking the most of the time. And let's go into the details. Scrolling down, we see that this time we've written to the storage, to the drive, way more data. Before that, we were talking about 1 megabyte. Now we are having 673 megabytes. And this is significant value. This is the shuffling which we want to be aware of. So let's go into the details of the stage and scroll down. Well, first of all, we will notice that some tasks are having the yellow bar. And the yellow bar, according to the agenda, is the shuffle write time. And this is the indication for us that each task does not only spend a time on doing the calculations, but actually the tasks started to consume a time on writing the data to the storage for the purpose of exchanging it. So we start to see the impact. And if we scroll down, now we are having pretty significant number of data written to the storage by each and every task. 24 megabytes over here, and on the right 29 megabytes. And if we compare it with the previous one, previously we were talking about the kilobytes, and now we are talking on the megabytes. And here we have the example of the shuffling, which is actually already having the impact on the performance. Let's get back to the notebook, and I have one more query, and the last one in that notebook, and this is sorting. So sorting should be prohibited in data engineering work. So what we are doing here is we are reading the same data and then order by a trip distance. And then if I hit explain, what we are going to see is similar query, file scan, exchange, and sort. And if I scroll down to the query results, that's how it looks like. It took 40 minutes to order it. So whenever we can avoid sorting data, that's something what we should do. And let's go and see the details of the job 13, 14, 15, and 16. We see actually 3 jobs which took significant number of time. Let's check out the one which took the most, 16 minutes over here. So let me click it, scroll down. So only this job wrote to the storage more data than we are reading from the file. It wrote for the purpose of shuffling, it wrote 37 gigabytes. So you see how complex the shuffling can get. And let's get into the details by the curiosity to see how it looks like. And if I scroll down, well, we see that actually tasks spend more time on writing the data to the storage for the purpose of the shuffling than the computation itself. So it's pretty impressive. And if I scroll down further, I see that the task which wrote the smallest number of data, it was already over a gigabyte, and the one which wrote the most of the data, almost 2 gigabytes. Let's do one more thing and see how we can check the same in SQL DataFrame Tab. And 13, 14, and 16, that's the one which is interesting. Duration 30 minutes. Okay, so that was our execution plan. And if I go and check, let's see the exchange over here. And we see that shuffle bytes written total 37 gigabytes. And the total number of time the task spent on writing at the drive over 1 hour. So you see that how you can think of a kind of simple computation like the order by can generate a massive data shuffling, and what a big impact it can have on the performance. And before I will close that notebook, let me one more time pay attention to the number of the partition. We are talking about partitioning of the data, usually twice in Apache Spark. First of all, when Apache Spark read the data from the storage, then we were talking multiple times that a driver check out the data and decide how to split it into partitions. But there is also a second moment when we are frequently talking about the partitioning of the data. It's when there is the data shuffling happening. The default number of the partitions when the data shuffling is happening is 200, meaning whenever we have data shuffling, Apache Spark will try to divide it into 200 partitions and distribute it. And here, this is the introduction to the next part, which is about the optimization. We are going to see a mechanism which is deciding on the fly what's the optimum number of the partitions, not to keep it 200 all the time. And in our case, it has decided that the 4 number is the optimum number of the partitioning for the data shuffling. So it has decreased the number of the partitions, but more about that in the next notebook. Let's get back to the disk, and to sum up everything, so we already know how to check a data shuffling in Apache Spark UI. We saw the impact on the performance, which can be tremendous, even with the simple operations like the group by. Similar case can come with the merge operation. And we also saw that the data shuffling does not only depend on the transformation, but also on the type of the data by executing the same query 3 times, just changing the type of the column from low cardinality column to the high cardinality column. Key points to remember. Shuffling is the process of redistributing data across partitions and typically involves data exchange between the executor's nodes. It requires saving data to the disk, sending that over wire again to the disk, and only then can be read into the memory, which of course is slow. Data shuffling can be very expensive, as we have seen. Sometimes it can be mitigated or avoided by even a code change, like for instance avoiding sorting the data. Nevertheless, it's often necessary evil. Ladies and gentlemen, let's touch on the optimization topic in Apache Spark. And optimization in Apache Spark Architecture, it's a massive thing. And you as the user can do a lot to optimize your flow, what will be discussed in separate movies, including choosing the right format to keep to store your data, like a Parquet or Delta format instead of the CSV, especially Delta format is so way more optimized than the CSV. Avoiding expensive operations like sort, which we already know that is generating massive data shuffling. Minimizing volume of data, caching data frames, repartitioning, avoiding something what is called user-defined functions. Again, a separate movie about that will come. Partitioning or indexing data, bucketing, optimizing cluster itself, and so many more things, which we will discuss in details. Nevertheless, what is important at this stage is to understand that Apache Spark Architecture is designed in the way to do a lot of things for us already, including Catalyst optimizers, which we have mentioned a couple of times already, but also something new, what is called Tungsten, which we didn't touch on, and we will say a couple of words about it, or adaptive query execution, which also works for us a bit in the background. Talking about the Catalyst optimizer, whenever we have a SQL query or some code using DataFrame or Dataset, the first thing which is generated, it's called unresolved logical plan. And the first step for the Catalyst optimizer is to check if the tables we are using in our query or the code, columns or functions are actually being registered in the catalog. If they are not registered in the catalog, we will get an error. If those exist, logical plan will be generated. Then a Catalyst optimizer is doing a couple of things for us, like a constant folding. So if we are having some constant in the code, it will replace it in the values, or predictive pushdowns or projection pruning, meaning pushing filters and select as early as possible to minimize volume of data is being read, and it's generate optimized logical plan. And with optimized logical plan, it's generate different possibilities to execute that plan, including different strategies to perform joins, and then calculates the cost model for each of it, checking how much data will be read with each physical plan, how much network movement will be done, or how complex computations are. So it calculates the cost model for each physical plan, and then it selects the most optimum physical plan, and voila. Tungsten, it's a bit of different beast. The goal of Project Tungsten is to improve Spark execution by optimizing Spark jobs for CPU and memory efficiency. So Catalyst optimizer, as we have seen before, generate optimized execution plan. Tungsten, on the other hand, it's used to generate optimized code using whole stage code gen, which we have seen many times in the execution plan already, and improve how the data are being handled in the cluster. So comparing to the Catalyst optimizer, Tungsten optimizations are just way closer to the bare metal. And the last theory before jumping into Databricks and seeing things in action is called adaptive query execution. And this is actually very interesting optimization approach, which makes sure that your application is not optimized only once at the beginning, but once your application runs and Spark collects more and more information about the data, about the operation, about the cluster behavior, it reruns some elements, recalculate the optimizations, including Catalyst optimizer. So the Catalyst optimizer will not be run only once at the beginning of your application, but if the application is long enough, it will be run multiple times. That's why sometimes we will get multiple jobs, and in each job we have only one stage, because after that one stage, adaptive query execution was triggered, the Catalyst optimizer recalculate everything once again, and that has created a new job, which we are going to see that in a second anyway. And this will involve dynamically change sort merge into the broadcast hash joins, dynamically decrease number of the partitions, dynamically handle skews, dynamically detect and propagate empty relationships. And we are in the optimization notebook. We are going to see in actions three main optimization mechanisms in Apache Spark Architecture: Catalyst optimizer, and adaptive query execution, and a Tungsten project. Not all the details, but enough so we can understand the concept. So starting with Catalyst optimizer, we have spoken about Catalyst optimizer quite a bit already. And we know about its lazy evaluation feature, and we saw it in action. Here we have another feature in action, which is called predictive pushdown. So already here, before executing the query, Apache Spark has figured out that it would be way better for everybody if we could read from the storage only the data about the fair amount, because nothing else is being used. And the example of how this is happening, it's over here. Apache Spark is doing this predictive pushdown by trying to read from our files only the fair amount column. Just in this case, we are keeping a data in the CSV. CSV is a row-based format, therefore there is no really option to read a specific column. That's why it's way better to keep a data in Parquet or in Delta format, which is fairly the same. Both of them are column-based types, and in such a case Apache Spark could actually read only the specific column which he would need for the computation, like over here. Moving forward, adaptive query execution. So let's at the beginning turn it off, and we can turn it off just for the purpose of the demonstration. In the production there is no purpose of doing that, by setting up the variable Spark SQL Adaptive Enable to false. And if we run our query, this is what we are going to get. And I'm curious if you are going to spot the difference, because we were running that query already before. So we got two jobs, 18 and 19. Let's see how those looks like. So job 18 and job 19. So it's over here. The one which took the most of the time was job number 19, and seeing the details. So for the first time, we can see two stages in the job connected with each other. Stage number 23 and stage number 24. So we are scanning the file, having the whole stage code again, which is the results of the Tungsten project. We will talk about it in a second. Then we have the exchange, and we are reading the data and doing another computation. And if I scroll down, I see details for both those stages. So below we have stage number 23, and we see that we have read around 11 gigabytes of data. Then we see that we have a shuffle of writes, so we've wrote to the disk around 1 megabyte of the data. And then a second stage starts, and we have read also around 1 megabyte of data. So we wrote it and we read it in the next stage. What is interesting is that we have 200 tasks over here. So going into the details of stage number 24 and seeing 200 tasks. And that's how it looks like. And we have all colors of the rainbow. And those are our 200 tasks. So actually the reason for having 200 tasks is because the data by default are being partitioned into 200 partitions when they are shuffled. And without the adaptive query execution, there is no mechanism in place to consolidate those and to request Apache Spark to minimize the volume of it. And if we see on how the tasks spend their time, is we have here orange, and orange is shuffle read time. Here we have a green, we already saw green before, and we have some blue, scheduler delay. We have some orange, and the orange is task deserialization time. So you see what's happening without adaptive query execution mechanism turned on, which is pretty recent. And if we scroll down, we see all the details for all those tasks. We can also go to the SQL DataFrame tab and find the same job number 19, which is over here. And let's check how this looks like here. So what is different is we don't have anymore a block which was representing action taken by the adaptive query execution. Therefore, we are doing the exchange. We are partitioning the data into 200 partitions, but there is again no mechanism to decrease the number of the partitions. If we take as the comparison the previous query where the adaptive query execution was on, like this one, we are going to see that we had the exchange, we had 200 partitions over here, but we had adaptive query execution shuffle read, which collapsed that into the 4 partitions. So that's one of the big difference. Another difference will be visible once we will turn it on. So Spark SQL Adaptive enabled true, and run exactly the same query one more time. You can probably already see a next difference. Here we were having 2 jobs, 18 and 19, and here we are having 3 jobs. The reason being is that adaptive query execution, as the name suggests, it's something what is being used by Apache Spark during the runtime, which it means that it's not anymore just run like a Catalyst optimizer at the beginning of the query, but it's being run between the jobs, and it can trigger Catalyst optimizer one more time, or collapse the number of the partitions, and that happens over here. As we can already see, there is no stage including 200 partitions, and checking job 20, 21 and 22. So let's get back to the SQL and the DataFrame tab. 21, 22, that's the one. We can see exactly the same schema, just this time with collapsing the partitions from 200 into 1. In our cases, we are not using the massive volume of the data, so the difference in the performance may not be so visible. But on the production, if you try and turn it off, you will quickly appreciate it. Okay, let's now talk about the Tungsten project. So Tungsten, as we've spoken, is way closer to the bare metal. Purpose of the Tungsten project is to introduce a set of optimizations into Apache Spark Architecture related with the memory usage optimizations or CPU usage. One of the examples of the Tungsten in action, we will see if we will turn it off. And we can turn it off, or different parts of it, we can turn it off. And here we are turning off the optimization, which is about generating optimized code for each and every tasks. So if we run exactly the same query without Tungsten project turned on, and we go and check job 23, 24 and 25, so let's open this one more time, and jobs 23, 24 and 25, and as usual taking the one which took the most of the time. What we are going to see, we don't have here anymore whole stage code again. Instead we have hash aggregate. If we compare it with previous jobs, like this one, then we can remember that always previously we were having the whole stage code again. It means that Tungsten project, when it's on, it generates optimized code for each and every task on the fly instead of using the generic functions, like over here. But again, the benefits of all those free optimization mechanisms in Apache Spark Architecture we will appreciate only once our data will get big. And we are at the end of introduction to Apache Spark Architecture. Congratulations! We have learned a lot of new concepts, and some of them were not really easy. The most important step is to practice. Every time you write a query, just try to open Spark UI and try to figure out what's happening under the hood. Meantime, don't forget to subscribe to the channel because there is a lot of new cool content coming shortly. See you soon!